In Module 3.7, we're going to examine the log normal distribution, and specifically we'll also look at doing numerical integration in a variety of different contexts, which both of these concepts are used widely throughout the book. In order to understand the normal distribution, we will contrast it with the normal distribution. So basically, we'll look at two different distributions, the log normal and the normal. That we're going to begin to get quite technical and take a deep dive into these properties. There's several properties of the log normal distribution that I don't think most quantitative financial analysts really understand, and it's caused problems in some of my work in the past. And so I'd like to just rummage around for a while in these two distributions and understand some of the comparisons and contrast. And we'll end this particular module by looking at a bivariate normal distribution and some of its properties. Just by way of reminder, the cumulative distribution function simply is the function that generates the probability that some distribution's value will be less than some specified value of x. In a continuous distribution, is simply the integral from minus infinity up to x of the probability density function, which here is denoted at f sub cap x. And so both the normal distribution and the log normal distribution are continuous functions, and so this is why the role of integration comes into play. The log normal distribution is what's known as a two-parameter distribution. The limits of the mean are between minus infinity and plus infinity, not inclusive. The standard deviation has to be greater than 0. It can't be equal to 0. And one interesting and very profound observation on the log normal distribution is that the variable itself cannot be 0. It has to be positive and less than positive infinity. This is deeply important in finance because stock prices can, in fact, go to 0. And so we will model stock prices with the log normal distribution in many different contexts, but we need to always keep in mind that it does not admit the possibility that that stock price goes to 0. If I take the log of the log normally distributed variable, the natural log of becomes a normally distributed variable. So if x is log normal, then log x is normal. And so the ability to transfer between the normal distribution and the log normal distribution is very helpful. The CDFs and PDFs for the log normal distribution, I'm going to use capital lambda, and for the normal distribution, I'll use capital N, which is based on the decisions made many decades ago, primarily the Black-Scholes-Merton framework. They used ND for the cumulative distribution function of the normal. And so these two distributions are somewhat related. The integrand of these two integrals is the probability density function, which is simply a lowercase lambda and lowercase n. And so these are the two distributions that we'll be examining in some detail. The different properties, the median is the value, what's the value of x hat such that the CDF equals a half, whether I go from 0 up to x hat or from x hat up to positive infinity for the log normal distribution. For the normal distribution, this would be minus infinity. The median for the log normal distribution is simply e to the mu, and the median for the normal distribution is simply mu. The mode is the peak point of the distribution. And one interesting insight for the mode of the log normal distribution is that it declines as the standard deviation goes up. And so notice that the mode of the log normal distribution is e to the mu minus sigma squared, whereas the mode for the normal distribution is just simply mu. Finally, the mean for the log normal distribution is mu plus sigma squared over 2, and the mean for the normal distribution is mu. And so what we immediately see with the log normal distribution is as the standard deviation goes up, the mode declines and the mean increases. The variance for the log normal distribution depends on both the mean and the standard deviation, whereas the variance for the normal distribution is just simply sigma squared. Skewness for the log normal distribution, this is going to turn out to be positive, excuse me, and the skewness of the normal distribution is 0. Normalized skewness, often what we want to do is make this a unitless number, and so if we take the second moment raised to the 3 halves, we can normalize it, and therefore it's a unitless number and easier to compare. The normalized skewness of from the normal distribution is also 0. Kurtosis measures the peakedness of the distribution, or what's known in finance as fat tails. And again, it's rather complicated formulas. Often kurtosis is measured as in excess of 3. And so that's because the kurtosis of the normal distribution is 3 times sigma to the 4th. So in the normalized case, the excess kurtosis of the normal distribution is 0. And so this gives us a reference point to compare different kurtoses. Just to give you, motivate this by an example, suppose we assume some x is normally distributed with some mean, some generic mean and some generic standard deviation. Then y, if y equals e to the x, then y is distributed log normal with the same parameters. So in finance, we often assume the terminal stock price is equal to the stock price at time little t raised to the rate of return continuously compounded annualized times the fraction of the year that has elapsed between these two periods. The distribution of returns will be normal. Notice if mu and sigma are annualized, then to get the per period return, I would multiply the mean times the fraction of the year that has elapsed. In the case of standard deviation, it's the annualized standard deviation times the square root of time that has elapsed. And so the distribution of prices is log normally distributed with this parameter. Terminal stock prices. If I take the expectation of the terminal stock price, notice that it's S0 e to the mu plus sigma squared over 2 times the time that has elapsed. The variance is a little more complicated. In the case of rates of return, the mean is simply the log of the expected terminal payout divided by the initial price and then normalized by the time period that has elapsed. Variance can similarly be calculated. Just to motivate by way of an example, suppose we have a $100 stock price, time to the horizon is 1 year. We assume an annualized 12% return and a standard deviation of 30%. What we intend by this 12% is that the expected terminal price is equal to the spot price e to the mu hat t minus t, which would be $112.75. Notice there's 2 different versions for the mean, and this does cause quite a bit of confusion. And so the mean adjusted for this standard deviation is simply going to be 7.5%. And so you have to be very careful when people are referencing the mean. Are they referring to the mean of the normal distribution implied by rates of return, or are they referring to the mean of the log normal distribution? And so we can estimate some different parameters. I would encourage you to spend some time here making sure you understand these calculations, but I don't want to work through it at this point. I do want to get across some comparisons to make sure we understand how standard deviations affect the PDF and CDF. And so if we have increasing return standard deviations, the terminal stock price is increasing in the mean. It has a constant median, decreasing in mode, increasing in skewness. And what's interesting to me is it increases the likelihood of very low values. And so just to get this illustrated, this was done in a spreadsheet years ago. If I have these parameters, stock price of 100, horizon of 1 year, expected return of 12%, standard deviation of 30%, we get this familiar positively skewed PDF of a log normal distribution. If we estimate the CDF, we get this familiar ranges from 0 to 1 of the CDF. Now I pulled this range way out here because what I'm going to do is compare ever increasing standard deviations. And so if I step up to 80% standard deviation, if you'll notice the PDF is the positive skewness is getting greater. So if you compare the 30 standard deviation to the 80, you can see that this distribution is becoming increasingly positively skewed. And the mode is actually, it's hard to see, but the mode is actually collapsing towards 0. And so in this case, the mode was 98.51. In the case of an 80 volatility, it's only 43. And so you have to ask yourself, does it make intuitive sense that the mode would collapse with increasing standard deviations? If we step up to 130, you can really see this mode collapsing towards 0. It's now 8.93. A mode of 8.93 when I have a $100 stock is very difficult to justify with financial data. If I step it up even further to 180, you get a mode that's less than $1, and hence I want to begin to cast a little bit of doubt on how well the log normal distribution is suited for financial data in light of high volatilities. Some of the commodities that I've worked with in the past, like electricity, would have implied standard deviations north of 1,000% within the log normal framework. All that really means is that I've got the wrong distribution in modeling something like electricity. So we will, in the next part of this video series of Module 3.7, we'll look at one application of the log normal distribution, specifically computing the probability that a call option is in the money.